Okay, thank you very much. I want to thank the organizer for inviting me to this talk in Heidelberg. So in this presentation I will briefly review the evolutionary properties during the last stages of low and intermediate mass stars with initial masses from about 0.8 to 6.8 solar masses and ages from about 10 to the 8 to 10 to the 10 years. In particular, I will focus on the so-called asymptotic giant branch and post-asymptotic giant branch phases. So I think that in the context of the present workshop, the evolution of HB and post-HB stars are particularly interesting in relation to early-type galaxies, in particular, for instance, with respect to the origin and evolution of the hot gas, that might be at least partly due to the interaction between the ambient gas and the stellar winds emitted by HB stars, as investigated a few years ago by Bregman and Perrott, and we have listened to his talk now. On the other hand, it's also interesting to see that we detected a strong silicate emission in early-type galaxies belonging to the Virgo cluster at 10 micron, as you see here, and this is an indication of the presence of dusty, oxygen-rich mass-losing HB stars in these galaxies. So all these kind of works adopt some recipes to describe the HB evolution, in particular the HB mass loss rates, the duration of the superwing phase, the masses of planetary nebulae, and the expansion velocities. I think that another intriguing issue is the debated origin of the ionized gas in liners, and recently all the post-HB stars have been suggested as plausible and promising candidates to explain these liners observations, and maybe to be preferred against the low accretion rate AGMs due to the fact that the line emission flux well correlates with the luminosity of the galaxies, and the gradient distribution follows that of the stellar continuum. So, in order to test the post-HB hypothesis, I think it's quite important to understand how the rate of ionizing photons depend on stellar evolution. So here you can see the ionizing photon rates QH and also the ratio of Q helium over Q hydrogen as a function of age of simple stellar populations for different metallicities and also taken from different population synthesis models. So you can see here the contribution of massive stars, which drops, and at 10 to the 8th years of age, we have the contribution of post-HB stars that is coming up, and it flattens out at these typical values. So the agreement between different population synthesis models is qualitatively okay, but there are differences amounting up to 1 dex from one model to the others for ages older than 10 to the 8th years. So the differences in the ionizing flux for ages older than 10 to the 8th years can be ascribed to different reasons, in particular different treatments of the TP-HB phase and different treatments also of the post-HB phases. There are also other effects due to metallicity and initial mass function. In my talk I will preferentially concentrate on these two items, the first two. So let me just briefly give an overview of the evolutionary properties of the latest stages of low and intermediate mass stars. So stars with initial masses from 0.8 to 6.8 solar masses after the exhaustion of helium in the core start to evolve close to their Hayashi line, evolving on the asymptotic giant branch at increasing luminosity. The structure of an HB star consists of an electron-degenerate carbon-oxygen core surrounded by two nuclear burning shells, the helium and the hydrogen burning shell, and above there is a huge convective envelope that extends up to the photosphere. The HB phase is characterized by an intriguing complexity of physical processes, such as thermal instabilities of the helium burning shells that produce the so-called thermal pulses that you can see here, radial pulsation, unique nucleosynthesis mixing events, dust condensation and growth, and mass loss. So the mass loss is a very important factor which may lead to the end of the HB phase, in particular when the envelope mass is reduced down to 10 to the minus 2, 10 to the minus 3 solar masses. The star leaves the HB on a fast track at almost constant luminosity, which essentially correlates with the mass of the central star and at increasing effective temperature. The increasing of the effective temperature is due to the decrease of the envelope mass due to the stellar winds and to the advancement of the hydrogen burning shell. So when the envelope is reduced down to roughly 10 to the minus 5 solar masses, the star starts to, the hydrogen burning shell is extinguished, so there is no nuclear source, and the star starts to cool down on the white dwarf cooling sequence at the expense of the thermal energy of the ions. So there are two important facts that happens on the post-HB evolution as soon as the temperature increase, effective temperature increase above 30,000 Kelvin, and there is the onset of a weak but very fast wind that is radiation driven on ultraviolet lines, and there is also the starting of the ionization, the emission of strong ultraviolet flux that can ionize the circumstellar envelope, and under particular conditions this envelope will shine as a planetary nebulae. So this is the canonical post-HB evolution, but we can have also other channels along which low and intermediate mass, low mass stars can evolve in the blue part of the HR diagram, becoming potentially high ultraviolet emitters. In particular, we may have helium burning stars, post-HB stars, so the nuclear source is not hydrogen shell, but the helium burning shell. They are characterized by these loops. Then we may have post-LHB stars and HB Manchet stars. In particular, for these two other classes of stars, you see here in red and blue, these are the result of an insufficient envelope, maybe due to RGB mass loss, so that they are not able to complete the full HB evolution, and they will start to move on the blue part of the HR diagram before, in particular, the HB Manchet will evolve from the blue horizontal branch region to directly on the white dwarf cooling sequence. And please take note that the evolution timescales are quite different. So going back to the canonical post-HB evolution, models predict that the rate of ionizing photons depend on three main parameters: the luminosity of the central star, the effective temperature, and the evolutionary speed. So the rate of ionizing photons is expected to increase quickly up to a maximum in correspondence of the knee of the post-HB tracks, and then you have a slower decrease due to the deceleration of the evolutionary speed. In these tracks are color-coded according to the time scale in units of 10 to the 30 years. I'm going now to discuss three main parameters that control the post-HB evolution. Namely, the first one is the mass of the central star. A direct constraint on the mass of the central star comes from the semi-empirical initial final mass relation that is based mostly on 62 white dwarfs, mostly in open clusters. So you see that there is a clear positive correlation between the initial and final mass, that is the mass of the white dwarfs, although there is also a very large scatter. And in particular, I want to emphasize that we know very little about the low mass end of this relation that is most important for the studies, for instance, of elliptical galaxies. So what are the factors that control the final mass of an HB star? So the final mass depends on the core mass growth during the AGB evolution. So the first factor that affects the core mass growth is the mass loss. They are stellar winds. The longer will be the AGB lifetime, of course, the larger will be the final mass. Observationally, there is a very clear dependence of the mass loss rates on the pulsation periods of long period variables, AGB stars. In particular, it is seen a very clear exponential increase of the mass loss rates along the AGB, with typical mass loss rates ranging from 10 to the minus 8 to 10 to the minus 6 solar masses per year, until the mass loss rates seems to flatten to an almost constant values, characteristic 10 to the minus 4, 10 to the minus 5 solar masses per year, which correspond to the superwind and the planetary nebulae ejection, as you see here. These are the typical expansion velocities that are observed in these outflows, ranging from few kilometers up to 20-30 kilometers per second. So on the theoretical ground, the situation is more difficult. So there are many uncertainties. It's very difficult to model the mass loss. And up to now, we do not have yet a robust description of mass loss from first principle. The second process that affects the final mass of the star is the so-called further jump. It's a sequence of mixing events that take place as thermal pulses. And when the convective envelope at thermal pulse is able to penetrate inside the intershell region, you expect that the chemical discontinuity is shifted inward, and so this determines an almost instantaneous reduction of the core mass. And you see this like trend that is given by this intermittent occurrence of thermal pulses and the jump. Theoretically, due to a very unsatisfactory description of stellar convection, the efficiency of this process is very, very uncertain from first principle. And so we have different predictions from different models that can vary quite a lot. So in this context, and also motivated by other important astrophysical reasons, I think that the bottom line is that the AGB phase needs to be calibrated. And we have recently received a major funding from the European Research Council to improve on this aspect. So we are now using sophisticated stellar AGB models in combination with high-quality data to calibrate this phase. In particular, we are using data from the ANS survey, also FET for M31, and also new discovered white dwarfs who put constraints on this particular phase. But coming back on the factors that affect the evolution of the core mass, the second factor, is the evolutionary speed that characterizes the post-AGB evolution. So we have different evolutionary speed depending on the treatment of the stellar winds and the fast wind. And in fact, this time, in particular the transition time from the end of the AGB up to the ionization, and then also the crossing time, depend on the erosion rate of the envelope, and in particular on the mass loss rate, which is very uncertain. So we have quite different predictions from author to author, also for the same stellar mass. And the prediction can vary by factors of few, so it's still unconstrained. And the third, I think, factor that is important that affects the post-AGB evolution is the dominant nuclear source during the post-AGB evolution. So, since during the AGB the two burning shells alternate as dominant energy source for these stars, it happens that the luminosity and the evolutionary speed on the post-AGB depends on the phase of the thermal pulse cycles at which the star leaves the AGB. So if the star leaves the AGB at, let's say, pulsation phase cycle larger than 0.25, 0.3, the star is expected to be hydrogen burner, so with the hydrogen burning shell active, whereas in the opposite case, at lower phases, the star will be helium burner, and there are important differences in the post-EGB evolution, in particular the helium burners that account roughly 20% of the total post-EGB evolution will be more prone to experience a late thermal pulse with this very complicated evolution on the post-EGB. So the star is brought back to the Hayashi line. The helium burning tracks are characterized by a slower evolution, and they are also less luminous than the hydrogen burning shell. So in terms of ionizing flux, there are differences. So I made this very simple experiment. I took 3 post-EGB tracks for the same center star mass of 0.6 solar masses, 1 helium burner, 1 hydrogen burner from the same set of models, and another one from another set of model, helium-hydrogen burner. And again, the colors indicate the evolutionary timescale in 10 to the 3rd year. So different models yields different timescales, and also helium burners have longer timescales. So it's interesting to compute now the cumulative number of ionizing photons for the 3 cases, and we see that despite of the fact that they are less luminous, helium burner tracks seems to emit more ionizing photons than the hydrogen burning tracks, in this case by a factor of a few. Compare the red or black lines with the blue line. So these are effects that one should consider when computing this kind of things in stellar population models. I made also an analysis about the possible dependence on the flux of ionizing rates on the initial final mass relation. So I took 3 semi-empirical relations from the literature, and we computed the stellar isochrones and the ionizing photon fluxes for different metallicities from very low to high with the Padova stellar evolution tracks. And in these 2 panels you see the differences relative in index, and so we expect quite large differences at younger ages where the 3 initial final mass relation deviates more, but there are also some differences that affect the older ages, even if, as I told you, this part is poorly constrained by the empirical determinations. And finally, I try to address a little bit the issue about the contribution of EGB stars to the mass injection. And so this can be done quite simply with some recipes, but now it is possible to have detailed estimation based on EGB evolutionary models. So in practice we can calculate the evolution up to the complete ejection of the envelope for all masses that are relevant for the EGB and post-EGB evolution for many metallicities. So we can produce thousands of EGB tracks. This is an example of the sample output for a particular model. And so you see we can predict the mass loss rate, which is modulated by the occurrence of thermal pulses. So starting from these models, we compute the stellar isochrons, and we can compute the specific rate of mass loss from simple stellar populations for different metallicities and as a function of the age. So there is a clear hint of a decreasing trend at older ages, but you see that when you consider the complex evolution of EGB stars inside your modeling, you also expect large fluctuations in this kind of models due to the complex behavior of these tracks. And then if we focus now on the oldest part here of the simple stellar populations, we can estimate the mass injection rates in elliptical galaxies. So here I did some comparisons for the specific mass injection rate taken from 2 sets of TP-EGB tracks, and these are the 2 results that we obtained, and we can compare these theoretical predictions with the measurements of 9 elliptical galaxies taken from this work of Afi et al. 2002. And so we can compare and see that the models give, the oldest model seems to overproduce the mass loss rate injection. The newer model seems to be in more agreement, but the message is that we can now do this kind of calculations with more detailed models, and there is an ongoing calibration so that we may have also better results soon. And we can compare also this kind of theoretical prediction with the mass loss rate due to supernova type 1a, which is quite lower. Okay, so I come to my conclusions. I think to have convinced you that the details of AGB and post-AGB evolution play a critical role when one tries to investigate the feedback of these type of galaxy properties. The AGB phase is characterized by many uncertainties, and so the AGB calibration is really urgently needed, and also new post-AGB models are needed because the default ones that all we are using date back to 1994, so they're quite old. The ionizing photon rates depends on, particularly on the initial final mass relation, the nuclear source that is dominant on the post-AGB and also on the crossing times. And concerning the AGB mass loss injection, now we are in the position to produce realistic, more detailed predictions about the contribution of AGB stars over a wide range of ages and metallicities. Thank you very much.
Take this opportunity to ask a question first. You showed that the mass injection rates have come down quite a bit. So
Yes.
what fraction of the total return fraction that people normally have in cell population models, the mass of a given amount of stars formed that returns to the ISM over a large time, is due to this planetary nebula? In other words, how big a contribution is this?
Well, I didn't do this computation with the latest tracks. So concerning this old population, I think that the dominant contribution is due to the AGB stars, not on supernova type 1a. Depends on the age, of course, on the galaxy that you are considering. I had to, these are very not preliminary, but I mean, I produced these results just for the workshop, and I had to go back to the tracks and also to check. But in any case, we are calibrating these kind of things on observations of...
So if this is the dominant effect, then basically when people say after about 10 gigayears, 40 or 40% or something, or 50, even larger, had this returned, you're claiming that 40% has become like 4%?
No. Most of this is instantaneous, and most of that return comes from type 2 supernova.
No,
That's
above
above.
10
Sorry,
This is the
no, it comes from the
It comes all from AGB essentially.
Yeah.
The RGB must be losing
The
mass.
stellar, the mass fraction above the
At these
solar
ages,
mass
yeah.
is very small. Right?
But the RGB must be losing mass as well.
Yes, but the amount, yes, there is, it lasts long,
But
but
if
the amount of...
instantaneous comes down by a factor almost 50 from 4 to 12 gigayears, then integrated it must also come down.
I have to say that this also, I didn't put many other plots, but this also depends on metallicity. So this was for solar metallicity. If I use super solar, I get higher mass loss. So there are also
not by factor 10 from your plot.
No, okay. In fact, I have to check this result because we adopted different mass loss prescriptions, and the lifetimes of the AGB now that we are calculating are lower. You know that the AGB contribution was quite overestimated in the last years, in the last population synthesis models. Now, with the calibration, it comes down also in terms of lifetimes.
Even in BC03, it was overestimated? I know Maristan overestimated it, but BC03 I thought had it about right for the wrong reasons.
Yes, it is. In terms of lifetimes, yes, but for the mass loss rates,
Understood.
I don't know.
Jay.
Yeah, I think maybe we're mixing two things here.
Yeah.
There's the luminosity of the AGB, right? There's the remnant white dwarf mass. The stellar mass loss rate in an old population is essentially the turn-off mass minus the white dwarf mass.
Yes.
That gives you the fraction.
That's right.
Yes,
Independent
yes.
of the details of the AGB, except insofar as it changes that final white dwarf mass, right?
Yes.
So have you changed the final white dwarf mass, and does it match the solar region distribution?
That was my question.
Yeah. So,
It wasn't.
and then the second question, which is different, is how long do you spend in what stage in an AGB to contribute to the spectral energy distribution? Really tough question, right?
Well, the major contribution of AGB stars peaks at roughly 1 giga a year. When you have largest contribution, for instance, in infrared luminosity, as shown also from the Magellanic Cloud clusters. So that is the bulk of the RGB contribution in terms of integrated luminosities. Okay, so then we have a decaying trend at younger and older ages.
What about the first
30%.
part?
Sorry.
So the white dwarf mass
Yeah.
is the key here. It
Yeah.
tells the return mass fraction.
Yeah, yes, but yes,
Total, from a population sense, not an individual star sense.
yes,
So you can test the model to some degree by asking, what is the distribution of white dwarf masses,
yes,
solar neighborhood, in globular clusters, etc. And that seems to have a peak around 0.6 solar masses, which is where this 40% comes from. It's a very rough number, it could be 30%. But it doesn't change by very much, unless you change that white dwarf mass up.
yes. But in globular clusters, the mass of the white dwarfs is typically lower.
Well, 0.5, but
Yes,
it's
yes,
not 0.7, so the fraction's about the same.
yes. So maybe the effect is lower in terms of the mass of the white dwarf, but it might be larger in terms of integrated luminosity, depending on the lifetime. That may change quite a lot.
Gotcha.
And one more question, Glenn?
So, you talked about the ionization rates. Could you also tell us roughly how hard the ionization can be? I mean, how many Rydbergs can you go with?
I'm sorry. Can I go back? I don't know, to be honest. I know that the... Sorry, where is it? No.
Yeah, well, that looks good.
Where is it? So this is a measure of the hardness of the spectrum, this ratio. Okay, I saw that typically it reaches 0.6, this ratio, and it was in agreement also with the calculations made by Sid Fernandez and Sadinska. So these are so in any case it's much harder than the spectrum provided by massive OB stars that you can see
So
in
do
this
you
part.
have so there's a good prediction of how the spectrum looks like of these.
This is what we get with the latest models, yes, and they are consistent also with other population synthesis predictions in general. These are the typical numbers that we get.
Okay, one quick question, and we move on.
Quickly ask, connected to this, do you expect that the extreme horizontal branch stars have much harder spectrum than the post-AGB because they've lost more of the atmosphere?
Well, I think that in terms of the spectrum, maybe yes. Let me see here where it is. I don't have any, it's only the evolution. Well, in any case, what I was trying to say is that despite of the fact that these AGB Mankay stars are less luminous, they reach quite high temperatures and the evolution timescale is higher, so the integrated contribution can be important.
Yeah.
So now I do not have quantified, to be honest, this contribution. But we can do with our models, we can do easily. So it's something that we can implement.
Okay, thank you, Paola.